Okay. So, last time we proved that Brauer group of any field K is isomorphic to the second Hall homology. Okay, SEP over K with coefficients in the multiplicative group. For example, if Brauer group of a finite field is second Galois homology of Z hat, this coefficients in torsion Galois module. And we discussed that for torsion Galois modules, only H1 can be non-zero. So this is 0. So we proved that every division algebra over a finite field is commutative. Okay. So now our goal is to prove that the Brauer group of the field of rational functions on a curve over an algebraically closed field is 0. So this will help us to compute higher homology of curves. In order to do this, so let's define a class of fields. So say that K is a CR field. R is an integer. If the following condition holds for any homogeneous polynomial, any homogeneous polynomial has with coefficients in K, say of degree f is d, and such that degree raised to this power is less than the number of variables. Has a non-trivial 0. So that means that there exists non-zero element A1, AN, let's call it alpha in Kn, such that f of alpha is 0. Okay? So, for example, we will be interested in the case when R is 1. And so, this K is a C1 field if every polynomial, homogeneous polynomial whose degree is less than the number of variables has a non-trivial 0. So the reason why we are interested in this is the following proposition. If K is a C1 field, then its Brauer group is 0. And proof is the following. So it's application of the reduced norm map. So let A be a central simple algebra, central simple, then then so we have A. We can embed A into A tensor with K sep over K. And this algebra is isomorphic to the matrix algebra. It's always split. And so let's consider the determinant map from this algebra to K sep. So so we have the composition that gives us a map from A to K sep, and I claim that it factors through K. Okay? And this is called the reduced norm map. So why it's factors? Well, so I claim that if I give myself any element of A, then its image under this homomorphism, well, first of all, this homomorphism, this construction depends on a choice, right? It depends on the choice of this isomorphism. However, any automorphism of this algebra, of the matrix algebra, is inner. In particular, well, and the determinant of the conjugate matrices, determinant of the conjugate matrices are the same. So in fact, the composition does not depend on the choice of this isomorphism. Moreover, so let's show that if I take any element of A, then its image here is Galois invariant. So I give myself some sigma in the Galois group. And then, so I have this arrow, and I also have, let's give a name to this. Let's go with, let's call it I. And I also consider the conjugate. I consider the composition of sigma and I. So this gives me two embedding of A into this matrix algebra, which consequently gives me two maps from this guy to this guy. And using the fact that any automorphism of this algebra is inner, it follows that these two maps are conjugate. So these two are conjugate. And therefore, if you use I composed with the determinant, you get the same map as sigma times I composed with the determinant. That means that the image of A here is Galois invariant. Okay? So I sigma composed with I determinant is the same as determinant composed with I. Because these two maps obtained by conjugation with the matrix in K sep. Does it make sense? Okay, and therefore we see that the image here is Galois invariant, and so it lands in K. This is called the norm map. And well, you see that the norm map is a polynomial function. in dim A variables of degree square root of dim A, which is n. So why is it, and the coefficients of these polynomial functions are actually in K. So what does it mean that it's a polynomial function? It means that you choose any basis, you write an element of A in this basis, and then it's a polynomial function in coefficients. So, well, why that? So I know that if I substitute elements of A, I get elements of K. So that means that if I So a priori, this is a polynomial function with coefficients in K sub, but I claim that in fact the coefficients of this polynomial are in K. This is obvious if K is infinite, right? Because if two polynomials are the same, if the polynomial and the conjugate polynomial have the same values at all elements of a vector space over infinite field, then the polynomials are equal. But if K is finite, then this is a matrix algebra, and then by the remark above. So then there is nothing to prove. So it's already, A is already the matrix algebra. Okay? So now let's use this observation to prove the proposition. So now let A be a division algebra. Ну тогда это уже матричная алгебра. Просто над К. И тогда отображение вот это вот отображение нормы, это просто детерминант над К.
В смысле, не нужно брать тогда?
Да, не нужно К себе брать.
То есть мы не можем получить, скомбинировать предложение с теоремой Вейля и
Ну, не знаю. Okay, so let's A be a division algebra. So dimension of D is n squared. So we want to show that, in fact, n is 1, right? So saying that the Breuer group is trivial means that there are no division algebras, central division algebras, other than field itself. And, okay, so we'll just apply, by definition of C1 field, apply it to this norm apply it to this polynomial that exists an element alpha in D star in D minus 0 such that norm of alpha is 0. But the norm is multiplicative. It takes product to product because the determinant does. And therefore, that's contradiction. Well, if n is greater than 1. Otherwise, you can't apply. So that's a polynomial in n squared variables of degree n. So if n is greater than 1, that's contradiction. Ну, вот мы нашли... Да, да. Okay? That's complete the proof. Лиза, у вас вопрос? Okay. So now I will prove that apply this to the field of rational functions on a curve. So let x be a smooth projective curve. I will always assume that it's by a curve, I mean that it's connected. And K is the field of rational functions. So this is K of x. Then K is a C1 field. Okay, so let's prove this. Proof is very nice. And this is an application of Riemann-Roch theorem. Well, easy part of Riemann-Roch theorem for curves. So what you do is the following. So you take, suppose you have a polynomial. So f of t1, tn. That's a polynomial with coefficients in this field of rational functions. Okay, so K are rational functions on my curve. So this every rational function is regular on an open subset, and they may have poles somewhere. So pick an effective divisor, divisor D, such that all these coefficients, let's say f is sum of a I1 in, ti1 tin, all these coefficients a I1 in are global sections of some of this line bundle. Oh, sorry, this is, let's call it H. So why can I do this? Again, so what are global sections of this line bundle? If H is an effective divisor, this consists of rational functions that are regular outside of this divisor, outside of the support of this divisor, and have some bounded poles, bounded order poles at the support. So of course, every function, every rational function, for every finite collection of rational functions, I can find such H. Ну вот вы возьмете коэффициенты. Вот какая-то первый коэффициент берете. Это какая-то рациональная функция. Она регулярна всюду, за исключением там 3 точек. И в этих точках она имеет порядок полюс 10-го порядка. Вот вы берете сумму этих 3 точек с коэффициентом 10. Хорошо? Very good. So then, for say let's now consider let's fix some integer e and consider rational functions of the form that are regular everywhere except for the support of this divisor H. And I assume that, so I fix some integer, positive integer e, and I consider this larger divisor. And I consider rational functions that, again, are regular outside of the support, and they allow to have poles of higher order at H. So is So if I consider this n tuple of rational functions of this type, then f of alpha. So let's see what is f of alpha. So I take this polynomial, and I substitute alpha I here. So I claim that so I can bound poles of this guy. So first of all, the poles are possible only at the support of H, because outside of support of H, all these functions are regular. Moreover, I can bound the order of these poles. These are gamma of x, though I have O of d times E plus 1 times H, right? Where d is the degree of my polynomial, right? Now, okay, now I consider the following equation. F of alpha is equal to 0. And I will try to solve this equation in, I will look at solutions to this equation. So my alpha is of this form where alpha I sits here. This is a finite dimensional vector space. So I can think of this as is a system of how many equations I have. So this is a vector in this vector space, system of this number of equations, or of 1 plus dE H equations of now let's compute the number of variables. So how much freedom I have. So my alpha I is any element here. So so that means that the number of variables is n times dimension of gamma x or of so E H and this number of variables. Right? System of homogeneous equation. These equations in this number of variables. Now, let's observe that let's compute these dimensions using the Riemann-Roch theorem. 1 plus dE multiplied by H. So Riemann-Roch theorem computes the Euler characteristic of a line bundle. But when H is very ample, or when E is large enough, this is going to be a very ample, well, this is going to be a very, well, this will have trivial higher homology groups. So by Riemann-Roch theorem actually computes this. So this is equal to the degree. Degree is equal to 1 plus d times E times degree of H, which I will denote by some, it's a constant, plus 1 minus g. where G is the genus. And this number is n times dimension of this guy of EH. By the same reason, it's equal to n times E times C, that's the degree, plus 1 minus G.
Сейчас, а мы использовали, что H это обильный дивизор?
Ну, мы использовали, что H эффективный дивизор, и E это очень большое число. Если, что нам говорит теорема Рiemann-Rocha? Нам говорит, что если степень вот этого дивизора больше, чем 2g минус 2, то высшие когомологии, первые когомологии отсутствуют. У H положительная степень. Это все, что нам нужно. Поэтому, выбрав E достаточно большим, вот это число будет больше, чем 2g минус 2, поэтому по теореме Рiemann-Rocha размерность равняется просто вот этому. Положительную степень имеет.
Ну, то есть первые когомологии заявляются...
Да. Ну, они не для любого обильного Арса, они заявляются для любого дивизора степени больше, чем 2g минус 2. Okay. So now, if E is very large, D is, remember that D is less than N. C это степень. C это степень H. Вот это число for E very large. This number will be greater than this one. Ну, потому что здесь коэффициент D, это примерно CDE, а это NEC. Но если у нас имеется такое неравенство, то для очень большого E это число будет... сейчас, простите, какое число будет вот это? Спасибо. Okay. So, therefore, so what we have? So we think of this as a system of linear equations with coefficients in our base field K bar, algebraically closed field. These are homogeneous equations, and the number of variables is greater than the number of equations. And by basic theorem on intersections in projective space, if you have this system has intersection theory in projective space, this system has a non-zero solution, right? Не, он не линейный. В смысле? Ну, как? Не линейный. Ну, например, если у меня есть система из 5 уравнений на 6 неизвестных однородная, то она всегда имеет ненулевое решение. Правильно? Потому что вы просто считаете пересечение многообразий в проективном пространстве, и пересечение всегда... Оно не может, во-первых, оно не пусто, а во-вторых, оно имеет не меньше, чем ожидаемая размерность. Okay, so I use here that the system is homogeneous. It implies that f of alpha has a non-zero solution. Okay? Good. So you can, as an exercise, you can modify this argument to prove that if X has is any scheme of an algebraically closed field, finite type, of dimension equal to R, then the field of rational functions is the CR field. But I will not use it. So let's combine these two propositions. So corollary, which is a theorem of Z, is that for every algebraic extension of this field of rational functions on a curve over algebraically closed field, the Brauer group of L is 0. Why that? So if you have a central simple algebra over L, it's defined actually over some finite extension of K, right? L is not assumed, it's algebraic, it's not assumed to be finite. But without loss of generality, I may assume that it's finite, right? Because any central simple algebra is defined over finite extension. But then... Нет, K это K это K of X, dim X is 1, and K is algebraically closed. So, but then, so if L is a finite extension, then it's itself the field of rational functions in a curve, right? Every finite extension of L of K defines me another curve, which is the normalization of X in this extension. So I can just apply the two propositions to the curve whose field of rational functions is L. Okay. So in particular, it shows that the Galois homology of L with coefficients in L in the multiplicative group is 0. And I want to use it. So I want to use it to bound homological dimension of the Galois group. So here is the proposition I will need. So assume, so let K be a field. And assume that it has the following property. Assume that for any algebraic extension, the Brauer group of L is 0. Then, well, first of all, for any torsion Galois module, G, and it's going to be the Galois group of K sep over K. Module M, its homology of this profinite group with coefficients in M, all equals 0 when Q is greater than 2. And the second assertion is that homology of G with coefficients in K sep star, they're all equal to 0 for Q greater than 0. So when Q equal 1, this is Gilbert-90 theorem that we proved. when Q is 2, this is an assumption, and the claim is that higher homology also vanish. Okay, so let's prove this. So the idea is, so what we know is that, so we know vanishing of this group for k equal 2, and we also know that vanishing of this group for all open subgroups of G, because we have this condition. So the idea is that this vanishing implies vanishing of this assertion for some m, namely for m of the form when m is a group of roots of unity of order L in K SEP. This will be done using the Kummer exact sequence. And we reduce the general case to this special using method of trace. Да. Значит, любой элемент убивается умножением на целое число, не нулевое. We discussed that for finite groups, so there are two kind of notion of homological dimension. So we will say that homological dimension, say, is equal to 2 if for every torsion module, this group vanishes when Q is greater than 2. This implies that for any module M, not necessarily torsion module, this group vanishes when Q is greater than 3. There was a trick with using the fact that M homology of G with M tensor Q is equal to 0. Okay, so in order to prove this, I want to explain what's called the method of trace. Since we need it, we'll use it many times in more general setting for Étale homology, so I will explain it in, so before I give a proof, so this is a digression method of trace. Okay, so it consists of the following. So suppose you have a finite Étale map. Then well, I claim that there exists, so we will define the trace map, and this is a map of morphism of functors. So I have the inverse image functor from shifts on X to shifts on Y, and I have the direct image functor. And I want to map it to the identity functor. That means that for any sheaf F, I want to construct a functorial map from this functor applied to F to F itself. So notice that this guy is right adjoint to F inverse. So by adjunction, I have a map in the opposite direction. So the trace map is kind of is a morphism in a non-obvious direction. Mm-hmm. Суммы. Сейчас мы это увидим. So, okay, so let's do this. Here is the definition. Да, Дима. Да? For Étale получше. So I have sheaves on X Étale, and I have sheaves on Y Étale, and I have two functors this and this. One functor is f rho star, and this is f inverse. Okay, so suppose I have a sheaf f. I want to construct a morphism of sheaves on X. So here is the definition of the trace. So first, for a small étale open set on X, such that, what does it mean by small? I mean that if I take this finite étale cover splits over U. Here is what it means. It means that if I take Y and restrict it to U, and the restriction means this, then it's isomorphic to U times a discrete set, finite set. Какая тут картинка? Ну вот у вас вот представьте себе, что у вас не этальная топология, а классическая. Но тогда у вас, вот есть у вас какая-то база X, и вот у вас есть разветвленное такое то есть не разветвленное, такое конечное накрытие. Значит, вот я беру какую-то точку и беру такое вот маленькое открытое множество, на котором вот это накрытие тривиально. Что значит, что оно тривиально? Это означает, что прообраз — это просто дизъюнтное объединение копий вот этого открытого множества. Это значит, по определению накрытия, конечного накрытия, у любой точки существует окрестность, что это верно. Но для конечного этального морфизма существует x можно покрыть такими открытыми множествами этальными, что это то же самое будет верно. Soгласны? Что? Ну, не совсем. Let's do this exercise. So if I take for u x, then this condition will not in general hold. Because, so your suggestion was, in order to construct such u, your suggestion is to, I'll write it here. So you take y times y over x. So the question is whether it's true that this is the same as y times a discrete set. Whether this, I think of this as a finite étale cover of y. Is it a split cover? Well, it definitely has a section, right? This maps to y. This maps also to y. So this has a section, namely the diagonal. So I can split off the diagonal. Yes, the diagonal is both open and closed, because it's open because it's étale, and it's closed because finite map is separable. So, but it's the remaining need not be a split cover. So if this were a Galois cover, then you would write. So, but in general, so what you're supposed to do, you take this y, okay, so over y, your cover kind of is disjoint union of a copy of y plus a cover of smaller degree. So you can construct examples of such u by induction, right? By induction on the degree. So, okay, so suppose I have an étale u with this property, then, so what is f low star of f inverse of applied to some sheaf f at u? Okay? So over u, my cover splits. into the disjoint union of copies of U. So this will be right here. So you take a sheaf here, you pull it back. So and then you take global sections on the preimage of this. But the preimage is just 2 copies of this U. So it will be f of U to the power S. You have as many copies as the number of elements in S, right? So this isomorphism depends on the choice of this trivialization. But now, now so our goal is to construct a map from this to f of U. So what can I do? I can take the sum. Okay, so now for such U that I call small, I constructed this map. And in fact, it doesn't depend on the choice of trivialization. Because if U is connected, then any 2 trivializations differ by an automorphism of this U scheme. And the automorphism is given just by permutation of this finite set S. And the summation map is commutative, right? It doesn't, if you permute the factors, it will not change. So this is well defined. And now, да, давайте я сначала сформулирую утверждение. Вот давайте вот это вот свойство U назовем, что накрытие Y в X, ограниченное на U, тривиально. Назовем, вот как-нибудь его обозначим. So, U over X with this property form a covariant sieve on X. So if you want to construct a map of sheaves, it's enough to construct just a morphism of, sort of precious restricted to any covariant sieve, right? If your space is covered by, say, 2 open sets, then in order to construct a morphism of sheaves on this set, it's enough to construct a morphism between these 2 sheaves restricted to each open set that agree in the overlaps. That's what it means, what's written here. So now, why it's form a covariant sieve? So I construct, in fact, I claim that I can find U with this property such that this map is surjective. And the sieve generated by this U, by this single U, will be a covariant sieve. So let's construct a U such that the map from U to X is surjective. So I will construct it by induction. I will first take U1 equal to Y. Then I pull back my cover to Y to U1. So this is over X. Here is a map to Y. To U1. And it has a section, namely given by the diagonal. Right? It has a section. Diagonal. And because diagonal is both open and closed, I can split it off. I can write it as U1, disjoint union, something else, W. Okay, so our cover pulled back to U1 is the joint union of a copy of U1 plus another finite total cover, W to U1, which has smaller degree.
So you see that X is quite compact.
Why?
I mean, degree might tend to infinity if X is very curved.
Okay, maybe, yeah. So quasi-compact. So W to U1 has smaller degree. Now you take you construct U2 mapping to U1 such that W times U2 over U1 is union of U2 plus something else, and so on. So all these maps are surjective. This is also surjective. This is U1 that maps to X. This is surjective. Then you have U2 that maps surjectively to U1. All these maps are finite total, and then you.
I think when we discussed why delta is closed, we said that X is separated. Some other words, some technical words.
Well, no, I think finite total morphism, finite morphisms are fine, and every affine morphism is separated. Okay, so we constructed this trace map. So again, on the level of fibers, so the fiber of this guy at every geometric point is just d copies, direct sum of d copies of fibers of F at the same geometric point. And this map on fibers is summation map. Okay, this is an important construction, and it has the basic property of this construction is that if you compose this trace map with the opposite obvious map from this from the identity functor to this guy, which is given by a junction with this trace map, then the composition is degree F, which I assume to be constant, times identity. That is because this first map on such U, so there is a map from F of U to this direct sum, which is the diagonal map. So the composition of this diagonal map and the summation map is multiplication by the cardinality of S, which is the degree. Okay, and why is it useful for us? Because now. Suppose we have any sheaf, so I can consider homology of this sheaf on F. I can map it using the first map to homology of X with coefficients in F low star, F inverse of F. And then I can map it to homology of back to homology of X with coefficients in F. And this has an interpretation. F low star is a finite, F is a finite map. So this is the same as, well, we proved it using properties of Hungarian rings, that this is the same as Y F inverse of F, right? I recall that this follows from the properties that for finite maps, this direct image functor has no higher derived direct images. So, so we have this factorization, and the composition by factoriality, the composition is degree f, multiplication by degree of f. So in particular, if this integer is invertible in f, right? It's a sheaf of abelian groups. If it's invertible in every abelian group, it's order, well, then it means that this map is injective. So we can embed cohomology of x into cohomology of y with coefficients in this sheaf. This is already interesting even if x is, if f is constant. And that's how we are going to use it. So now let's, with this preparation, let's prove okay, so I think so let's, sorry, I think I raised the proposition. We'll have to write it again. So what we are proving is that proposition, so we have K, we have for every algebraic extension, we have that Brauer group of L is 0, and we want to prove that for torsion M HQ of Galois group with coefficients in M is 0, provided that Q is greater than 2, and also HQ of G with coefficients in K sep star is 0 for Q greater than 0. Okay, there are two assertions. This is 2. So let's prove this using method of trace. So let's start by observing that. So let's consider 1, and so let's first observe that we know this statement for some m. Namely, I have an exact sequence, the Kummer exact sequence, K sep star, K sep star, and here I have mu L. This is the group of roots of unity of order L. And this is multiplication raising to the nth power. So if L is relatively prime to the characteristic, then this map is surjective, right? Because taking nth root is a separable extension. And therefore, this is a short exact sequence. And so it implies that cohomology of mu L with coefficients, well, cohomology of G with coefficients in mu L equal to 0, but it's also true since we assume that the vanishing of the Brauer group not only for K but for all for all algebraic extensions, it's true that this group is equal to 0 for all open subgroups and Q greater than 2. Okay, so let me explain again why this is true when H is G itself. Then you look at this short exact sequence and you look at the long exact sequence of the cohomology groups. What I'm saying here, is it? Сейчас, действительно, как же я это... Сейчас, значит, почему же... Сейчас, действительно, значит, что отсюда следует? Отсюда следует только вот это. Правда? Сейчас, вот это. А для третьих у меня уже ничего не получается. Или получается сейчас. Сейчас. Сейчас, одну секунду. Сейчас, на третьих там могло бы быть ядро. Сейчас. Okay, yes, so sorry. This is also only true for, as I said. And this is obvious, right? Because this group is H1 of K sep star is 0 by Hilbert-90 theorem, and Brauer group is also equal to 0. So from the long exact sequence, we derive this statement. Now, good. And so if you want to prove it for open subgroup, you just look at the finite field extension corresponding to this subgroup H and use this fact. Now, so this is when L is relatively prime to characteristic. When L is not relatively prime, you use the following. So L is equal to characteristic of K. Then we have short exact sequence Z mod LZ mapping to K K sep. And this goes to K sep under the Artin-Schreier map. So this sends x to the 8th power minus x. That's the map. And this is also this surjective. So that's a homomorphism. And therefore, it's a short exact sequence. And it implies, now, for any field, homology of Gala group G with K sep with additive group is equal to 0 when Q is greater than 0. And this implies that H Q of G with coefficients in Z mod PZ is 0 when Q is greater than 1. Okay, so this is true for any field K, and why this is true? So when Q is 1, this is a corollary of faithfully flat descent. So homology K sep torsors are the same as the risky torsors, sort of a point, they're all trivial, right? when k is greater than 1, well, you can either use the fact that I mentioned but didn't prove that homology, even in flat topology of every quasi-coherent sheaf, higher homology, well, that homology of every quasi-coherent sheaf in flat topology is the same as homology in Zariski topology. Or you can, for example, use a classical Falk-Galois theory. If you have a finite Galois extension, then finite Galois extension, like here, then L, view it as a modulo over the Galois group, is a regular representation. Homology of a regular representation is a projective and also injective object. Well, homology of a free module, group homology, is 0. Okay? So therefore, we have some vanishing. And now let's use it to apply formalism of trace to derive the general case. Okay. So is this part okay, or shall I kind of try to explain more why this is true? Okay, so so here is a so if you have so if gamma is a finite group, then homology of gamma with coefficients in I need here k of gamma. This is the group algebra. They're all 0. Why that? For example, by Shapiro lemma. That's the same as homology of... ну, он проективный, но, вообще говоря, мы берем производные от точного слева функтора. То есть, если бы он был неактивен, то все хорошо. Хорошо? И здесь важно, что гамма действительно конечная группа, иначе это было бы неверно просто. Иначе то же самое было бы верно, если я вместо групповой алгебры рассмотрю такую бесконечные суммы, функции на гамма. Okay, so this is trivial group with coefficient in k. Right? Because this is induced from the trivial representation. And this is Shapiro lemma. By the way, I should have mentioned that so we are going to apply the formalism of trace. So I explain what it means in general, that in the case when x and y are actually fields, so suppose I have y spec L, and this is X. This is my F, spec K. So sheaves can be identified with modules of the Galois group G, and this is modules over H, which is Galois group of K sep over K. So there are two functors. Yeah, over L. So this is subgroup. One functor is the pullback functor, F inverse. And so in this, under this identification, it corresponds to the restriction. Right? If you have a G module, you can restrict it to H module. And what is the inverse functor? Well, what is the low star functor? Что? So suppose I have a H module. How can you construct a G module? Induction. So this is induction, and from G to H, from H to G, and what is it? So if you want to apply it to some M, you simply tensor it M with okay, I will write two formulas for this. You can take either a home over K of over Z of H from Z of G to M. That's probably called co-induction. Or you can take tensor product, Z of G tensor M over Z of H. So whenever you have a group G and a subgroup H, there are two ways to construct a G module starting with an H module. Either taking this construction or this construction. When H has a finite index in G, which corresponds to the fact that this is a finite morphism, the two constructions are the same. So one of these functors, namely this functor, is always right adjoint to F inverse. And this functor is left adjoint. So in the case when the index is finite, left adjoint is equal to the right adjoint. So these two guys are the same. So, and in particular, you get this map just from a junction. And in fact, I haven't explained it here, but so we constructed this co-unit of that junction. In fact, there is also a map from identity functor to F inverse of F low star. There exists such a map. And so if F is finite at L, you can show that so F low star is both left and right adjoint to F inverse. Similarly to what we have in the case of Galois, F of points. Good. So now let's do the proof. Let's see. I think it's unrealistic to finish it in 5 minutes, so I think I better stop here and resume the proof well, next time. Что? В каком месте? Ну, вот в смысле здесь. Нет, здесь нету никаких условий. Кстати, давайте заметим, что вот лемма Шапира, да, лемма Шапира говорит, что вот на этом языке, она что, собственно, говорит? Что когомологии y с коэффициентами в любом f, они такие же, как когомологии x с коэффициентами в прямом образе. И мы доказали это для любого конечного морфизма из y в x. Правильно? Потому что мы доказали обнуление старших прямых образов. Но в случае полей это вот ровное утверждение про то, что когомологии с коэффициентами, вот то, что мы здесь использовали. Угу. Да, значит, я объяснил вот это, а я еще не объяснил, почему действительно я хотел доказать, вывести отсюда вот этот факт. Но давайте выведем его так. Значит, когомологии G с коэффициентами в k сеп — это что? Это предел по всем открытым нормальным подгруппам, значит, в G open normal HQ of G mod H with coefficients in K sep H. Mm-hmm. So this is a field extension, finite field extension, Galois field extension corresponding to this open normal subgroup. And the fact that I referred to, it's a theorem of Arsene, that is the following. So I have, let's consider this field. Let's think of this as a vector space over K with action of the Galois group G mod H. It's a representation of this group. And the claim is that this representation is regular. So in particular, combining this with Shapiro's lemma, you get that this is 0. And so how you prove this, by the way? How to prove that this representation is regular?
You take a random vector and you write the orbit, you write the determinant, which consists of all coordinates, and then you reduce this determinant to what we want determinant to show something.
Okay, this is one way of proving this, and another way of proving it is the following. So we want to show that two representations of finite group are isomorphic. As Dima suggested, let's tensor it with K sep. And let's first prove that these are K representations of this group. But let's consider it first as representations over this vector space. And then I claim that this fact is obvious because K sep times, so if you take this tensor product of fields, it's just a disjoint, well, it's a product of copies of this field, and the Galois group permutes these copies. So this fact becomes obvious. Geometrically, it means that if I take this cover and I pull it back to spec K sep, it splits into disjoint union. So the fact that these two representations are isomorphic is obvious, and now we have a following general fact. Suppose you have a finite group, and I have two K representations which become isomorphic over algebraic closure of my base field. Then I claim that the representations are isomorphic. And the proof uses, for example, one way of proving this uses Krull-Schmidt theorem. So if these two representations are isomorphic, then they are already isomorphic as over some finite extension, right? So you can take some finite extension. Что? Ну, тогда... И что? Да, хорошо, да. Можно взять в качестве K' вот это. Но я доказываю абсолютно общее утверждение, что про любые представления. Значит, тогда вот такие два представления, ну, они изоморфны над K'. Теперь, в частности, давайте про это смотреть так. Давайте, значит, вот эти два векторных пространства с действием группы G по H, они изоморфны. Векторные пространства над K'. Давайте забудем, что это векторные пространства над K', давайте про них думать как векторные пространства над K. Но они по-прежнему изоморфны, тот же самый изоморфизм. А теперь у нас, значит, давайте рассмотрим вот это вот представление G по H как K-линейное представление, Тогда это просто сумма нескольких копий вот этого представления, а именно столько копий, какова степень K' над K. А теперь у нас такое утверждение, что, допустим, что у вас есть два представления конечной группы, такие, что их десятые степени, то есть если я вот каждое представление 10 раз сложу с собой, становятся изоморфными. Тогда я утверждаю, что исходное представление тоже изоморфное. И это следствие теоремы Круля-Шмидта про единственность разложения в сумму неприводимых, в сумму неразложимых. Но там была бы некоторая проблема с несепарабельными расширениями. А вот это рассуждение, оно работает для любой конечномерной алгебры. Для бесконечной мерной оно неверно.